Now we're continuing to talk about motion through an electric field, and we're going to look into the conservation of energy. This is the way the textbook explains. I'm going to explain another way, the way that we learned from Physics 160 in the next page. So here, if a particle moves through a change delta V in electric potential without a net applied force acting on it, applying the conservation of mechanical energy gives the change in kinetic energy. Okay, and that is change in kinetic energy equals to negative Q delta V, and since delta V is final minus initial potential, you can write it that way. So the couple things here are mechanical energy is usually shown with delta E, and that is delta K plus delta U. And we're saying that this is conserved, so that's going to be equal to 0. That's why delta K is equal to negative delta U. And what is negative delta U? It is negative Q delta V, right? So this part is really negative delta U. Okay, when you put it on the other side, delta K plus delta U is 0. And that means the mechanical energy is conserved. Okay. And it says net applied force. There's no net applied force. We still have the electric force due to the electric field, but this means like there's no one pushing it, pulling it, or some sort of applied force. Okay, the net should be 0 so that you can do this. So there's no other work done by other forces, but electric force is doing work. But we are writing it in terms of potential energy form. I hope that makes sense. And work by an applied force, the next step. If some force in addition to the electric force acts on the particle, we count for that work. So delta K is equal to negative delta U plus the applied work done, and that becomes delta U becomes Q delta V, and it was negative. We keep the negative and plus work done by the applied force. So as I mentioned before, especially in mechanics, I don't really like how the textbook is giving you different equations like that. And remember, to avoid that, we start with the original equation. So that's what I want to explain now. We have delta K, delta U, delta I. So first term is kinetic, second term is potential energy. Third one is the internal energy, and that's equal to work done plus heat. Okay. In this, especially in this class, we don't have any internal energy. We don't have to worry about friction or anything like that. That was the molecular changes, so we don't really have them. And heat, we won't give, we don't have heat transfer here, so that's 0 as well. And so this is the equation. Okay, delta K plus delta U equals to work done. This part is the mechanical energy, that delta E that I was mentioning. So the book is telling you, basically, is if there is a work done by an applied force, say by applied force, then the mechanical energy is, the change in mechanical energy is going to be equal to the work done by the applied force. Okay, that's the last one we got up here. This is the last equation. And if there is no applied force, then this delta K is going to be equal to negative delta U. And again, let's note that delta U is Q is equal Q times delta V. Okay, so depending on if you have the applied force or not, then you may have work done, and that's equal to the change in mechanical energy. Okay, that's what we have on the left side. So delta K plus delta U equals to work done, and delta K, if you put delta U on the other side and write it in terms of Q and delta V, it becomes negative Q delta V plus work. And again, this work is applied force. The work done by electric force is kind of hidden in the form of the electrostatic potential. Okay, so it's in here, not in the work done by applied force. So in the problems, we're going to be like moving charges around, so there's an applied force. Or we're going to look into the cases when how much work is done by the electric field. Okay, so we're going to look into those, and there's some sign issues. So we are going to discuss those later on.